Imagine a black hole, an entity so powerful that nothing can escape its grasp, not even light. But what if we told you that they are not as invincible as they seem? Welcome to the paradoxical world of Hawking radiation. In the vast expanse of space, black holes are cosmic leviathans, their gravity so immense that they swallow everything that comes their way, even the very fabric of light. Their insatiable hunger has led us to believe that they are invincible, indestructible. But in 1974, a brilliant mind named Stephen Hawking proposed a radical theory that challenged this belief. Hawking postulated that black holes are not the eternal, unchanging entities we once thought they were. Instead, he suggested they could emit particles, a phenomenon that would later be known as Hawking radiation. This was a groundbreaking theory, one that went against the very fabric of our understanding of black holes. The idea that these cosmic monsters could emit anything was, to say the least, revolutionary. But what is Hawking radiation? Simply put, it's a theoretical prediction that black holes can emit small amounts of thermal radiation due to quantum effects near the event horizon. To put it in perspective, it's like saying that a locked box from which nothing is supposed to escape can leak out particles. This is a contradiction to what we've always believed about black holes, that they are cosmic traps from which nothing, absolutely nothing, can escape. To understand this, we need to delve into the realm of quantum mechanics, a domain where the laws of physics as we know them take a back seat and a whole new set of rules come into play. It's a world where particles can pop in and out of existence, where they can be in two places at once, and where the impossible becomes possible. Intriguing, isn't it? But how does this phenomenon occur? Let's delve deeper. To understand Hawking radiation, we need to enter the quantum realm. And in this realm, things can get a bit quirky. Here, we encounter a fascinating phenomenon known as quantum fluctuations. Now, imagine the void of empty space. In our everyday lives, we think of this as simply nothingness. But in the world of quantum mechanics, nothing is a busy place. It's buzzing with energy, a constant frenzy of creation and annihilation. Pairs of particles and antiparticles, let's call them twins, spontaneously pop in and out of existence. These twins, born out of energy, are like mirror images of each other. They're ephemeral, appearing and disappearing in a flash. But what happens when this fleeting dance of creation and annihilation occurs near the event horizon of a black hole, the point of no return? Well, black holes, despite their reputation, don't suck everything in. So, when a pair of these quantum twins pops into existence near a black hole's event horizon, something extraordinary happens. One of the twins falls into the black hole while the other escapes into the universe. This escapee, now a lone particle, is what we observe as Hawking radiation. But hold on, doesn't this mean that the black hole is emitting particles? And isn't that against the very definition of a black hole, a celestial body that doesn't allow anything to escape its grasp? Yes, you're right. But remember, we're in the quantum realm where the impossible becomes possible. The twin that fell into the black hole, the antiparticle, actually reduces the black hole's mass when it meets its matter counterpart inside. It's as if the black hole is slowly losing weight, shedding off particles in the form of Hawking radiation. So, what we initially thought was nothing, the empty space around a black hole, is in fact a stage for one of the most fascinating performances in the universe. This quantum quirk is the basis of Hawking radiation, making black holes not so black after all. Now, what happens when a black hole starts emitting particles? This question leads us to the concept of black hole evaporation, a phenomenon as mind-boggling as it sounds. You see, black holes are not the all-consuming monsters we once thought them to be. They are not eternal, and they do not keep growing indefinitely. Instead, due to a process called Hawking radiation, named after the brilliant physicist Stephen Hawking, black holes can lose mass. Here's how it works. Around the event horizon, that is the point of no return for anything falling into a black hole, pairs of virtual particles are constantly being created and annihilated. These particles are a quirk of quantum mechanics, popping into existence and then disappearing almost instantly. But sometimes, one of these particles falls into the black hole while the other escapes into space. When the escaping particle becomes real and takes energy with it, the black hole loses a tiny bit of mass. This process is incredibly slow. For a black hole with the mass of our Sun, it would take longer than the current age of the universe for it to completely evaporate. But eventually, as it continues to emit Hawking radiation, the black hole will slowly shrink. As the black hole loses mass, it also loses gravitational pull. The less gravity it has, the less it can pull in surrounding matter, and the less matter it pulls in, the less mass it has. It's a slow, self-perpetuating cycle that ultimately leads to the black hole's demise. So imagine this, a black hole, once a mighty cosmic beast capable of swallowing stars, reduced to a whisper of its former self, slowly fading away into nothingness. This means black holes are not eternal. They can evaporate away given enough time. It's a fascinating concept that challenges our understanding of the universe and opens up new, exciting questions about the nature of black holes and the very fabric of space and time. But don't expect to witness a black hole vanish anytime soon. That's because the process of black hole evaporation is a marathon, not a sprint, particularly for larger black holes. Imagine a black hole with the mass of the Sun. You'd think such a colossal object would burn out quickly, wouldn't you? But here's where things get interesting. The evaporation of such a black hole would take more than a Google years. That's a mind-bogglingly long time. How long, you ask? Well, a Google is a 1 followed by 100 zeros. To put that into perspective, the universe itself is only around 14 billion years old. That's a 1 followed by just 9 zeros. So, in the face of a Google, the age of the universe seems like mere seconds. It's an incomprehensible scale, a time frame that goes beyond human understanding. A Google years, that's a 1 followed by 100 zeros. Talk about a slow burn. Hawking radiation brings with it a mind-bending paradox. The information paradox, as it's known, is a conundrum that has puzzled scientists for decades. Here's the crux of the issue. Hawking radiation, the very energy that black holes emit, seemingly carries no trace of the matter it once devoured. This is a direct contradiction to the laws of quantum mechanics, which assert that information can never be entirely lost or destroyed. Picture this. A book filled with knowledge and information is tossed into a black hole. Over time, the black hole emits Hawking radiation, but this energy has no hint of the book's contents. It's as if the book and all its information has vanished without a trace, contradicting the fundamental principles of quantum mechanics. This quandary is known as the information paradox. This paradox continues to baffle scientists, making Hawking radiation a hot topic of research. Hawking radiation also poses a cosmic conundrum. As we delve deeper into the mysteries of the cosmos, we encounter a concept that challenges our understanding of black holes. A concept that might hold the key to solving the information paradox we discussed earlier. This is the soft hair theorem, a fascinating idea proposed by Stephen Hawking, Malcolm Perry, and Andrew Strominger. In the simplest terms, the soft hair theorem suggests that black holes might have what's known as soft hair. Now, don't let your imagination run wild. This isn't hair as we know it. Instead, it refers to zero-energy particles that exist around the event horizon of a black hole. These particles, or soft hair, are not just there for decoration. They are theorized to carry information, acting as the cosmic postman, delivering messages about what's going on inside the black hole. In this sense, the soft hair may hold the answer to the information paradox, providing a path for information to escape the black hole's clutches. But why is this a conundrum, you ask? Well, this is because the idea of black holes having soft hair challenges the no-hair theorem. This theorem, in stark contrast, posits that black holes can be defined by just three properties: their mass, charge, and angular momentum, implying they have no hair. So, on one hand, we have the no-hair theorem stating black holes are bald, and on the other, we have the soft hair theorem suggesting they might have a subtle fuzz. This discrepancy between the two theories stirs up a cosmic debate and puts us in a bit of a hairy situation. However, it's important to note that the soft hair theorem is still a relatively new concept. It's like a theory in its teenage years, full of potential but also full of uncertainties. It's under intense scrutiny from the scientific community as they work tirelessly to determine its validity. So while we might not have all the answers just yet, the soft hair theorem opens up a new avenue of exploration in our pursuit to understand the enigmatic black holes. The soft hair theorem is still under scrutiny, adding another layer of mystery to black holes. Despite its fascinating implications, Hawking radiation remains unseen. This unseen phenomenon, like a ghostly whisper in the cosmos, is elusive, not due to a lack of effort or technology, but due to its inherently elusive nature. To put it into perspective, let's consider this. Hawking radiation is made up of incredibly weak particles. These particles are so weak that they are dwarfed by the overwhelming cosmic background noise. It's akin to trying to hear a single whisper in the midst of a roaring concert crowd. To pick up on these particles, we would need an instrument so sensitive it could detect a single grain of sand falling to the bottom of the ocean from miles away. Moreover, black holes themselves are not exactly cooperative when it comes to detecting Hawking radiation. They are, after all, the epitome of cosmic camouflage. Their immense gravitational pull draws in everything, including light, making them virtually invisible against the backdrop of space. And the radiation they emit, it's like a mere wisp of smoke from a star-sized bonfire, easily lost in the cosmic cacophony. Adding to the complexity is the fact that Hawking radiation is not just a single type of particle. It's a mixed bag of photons, electrons, and positrons, each with their own energy signatures. To detect Hawking radiation, we would need to sift through this cosmic soup and identify these minute signatures, a task akin to finding a needle in a multi-dimensional haystack. However, despite these monumental challenges, the scientific community remains undeterred. Efforts are being made to develop sophisticated tools and techniques to detect this elusive radiation. Theoretical models and simulations are being refined, and new experiments are being designed. While we have yet to observe Hawking radiation, it has already revolutionized our understanding of black holes. This unseen phenomenon, a mere prediction from the mind of a brilliant physicist, has sparked a revolution in our understanding of the universe. It has opened up new avenues of research, challenged established theories, and continues to fuel our cosmic curiosity. And who knows, the day we finally detect Hawking radiation, it might just be the beginning of a whole new chapter in our cosmic journey. Let's recap the fascinating world of Hawking radiation. We began our journey into the cosmos, exploring the intriguing inception of Hawking radiation. This radiation, a prediction made by the brilliant Stephen Hawking, is an emission from black holes, those mysterious cosmic giants that have captured our imaginations for centuries. We dived into the quantum quirk, the seemingly impossible phenomena at the heart of this radiation. It's here where we encounter the concept of particle-antiparticle pairs, a dance of creation and annihilation at the very edge of a black hole, the event horizon. Next, we explored the evaporating giants. Despite their immense size and gravitational pull, black holes aren't eternal. Hawking's theory predicts that they slowly but surely emit radiation, leading to a gradual loss of mass, a process akin to evaporation. Then, we observed the slow burn. This evaporation process isn't quick. It's an almost imperceptibly slow burn over billions of years, a testament to the vast timescales the universe operates on. The energy paradox was our next stop. The concept of black hole evaporation led to the information paradox, a conundrum that challenges our understanding of quantum mechanics. If a black hole eventually disappears, what happens to the information it swallowed? We then faced the Cosmic Conundrum. Despite the theoretical predictions, detecting Hawking radiation has been a significant challenge. This elusive phenomenon remains unseen, yet it keeps tantalizingly hinting at its existence. Hawking radiation, a concept as elusive as it is intriguing, continues to challenge our understanding of the universe. It's a testament to the beauty of science, where even the darkest corners of the universe hold secrets waiting to be uncovered. Before we wrap up this journey into the enigmatic world of Hawking radiation, let's take a moment to reflect on what we've learned. We've journeyed through the realms of quantum mechanics, touched upon the mysteries of black holes, and grappled with paradoxes that challenge our understanding of the universe. But remember, science is a never-ending journey. Each answer we find leads us to new questions, each discovery opens up new mysteries. That's the beauty of this cosmic dance. If you've learned something new from this video, then please give it a like and share your opinions in the comments. We're always excited to hear your thoughts and engage in enlightening discussions. Don't forget to subscribe and press the bell icon for more such content. Share this video with your friends and families, and together, let's continue to unravel the secrets of our incredible universe. Until next time, keep questioning, keep exploring, and stay curious.